Hello, today I'll be doing questions on aqueous solutions. Okay, let's start with the first question. Let me find it. Okay, here. It says, describe the chemical tests that would allow you to distinguish between solid samples of the following beryllium salts. Barium salts. I can't read. So here are the salts. So there's barium carbonate, barium nitrate, barium chloride, and barium sulfate. Here, so we need tests to prove that each of these exists inside a solution. So we have to do it. So first, normally we just add water, and then we'll have soluble and insoluble. And let's see. Let's check our solubility table thing in the formula sheet. Let me find it here. So here, let's see, barium carbonate. Most carbonates are insoluble. Barium carbonate is insoluble. So barium carbonate goes here, and then we have barium nitrate. Let's see, all nitrates are soluble, so the ANO3 goes here. Let's see, barium chloride. It says most chlorides are soluble and except for silver. So this is here. And let's see, barium sulfate. So most sulfates are soluble and except for barium sulfate. So barium sulfate is insoluble. So that goes here. So that's the first test we'll do, and then we get two groups of soluble and insoluble. So now we have to further test each of them to figure out if each of these salts are inside it. So first, so these will become solids, and these will become aqueous. Wait, oh yeah, my bad. Aqueous solutions. Can't spell. Might be bad. Okay. Yeah, my brain's not working. Let's see. So let's just start with solids. Yeah. So solids. So one test we can do between barium carbonate and barium sulfate is that we can because we can try to add acids to them, and because there's a carbonate here and we can create carbon dioxide. So what we can do is, so let's just put in nitric acid, yeah. So because it works, and then so basically the equation will be like barium carbonate plus nitric acid, and that will become barium NO3. Wait, barium is that'd be 3 plus this is 2 plus, I get, wait, barium barium nitrate, yeah. Nitrate have plus, and barium have 2, so we have to put brackets and add a 2, and then that means, and then we'll have H2O and also carbon dioxide, H2O, so we'll just have two of these, and that would work. Yes, I think. Okay, yes, that's balanced, and that means plus that means that this is a gas, this is a gas, this is aqueous, so this is aqueous, this is liquid. So adding and then barium sulfate is not reactive, not that reactive, so it would nothing would happen. So add nitric acid, and then barium carbonate will become liquid, aqueous plus gas, while barium sulfate will be solid. Proven both. Okay, now we go back to the aqueous solutions. So we do so we've proven half of it, so we need the other 2 aqueous solutions, and those include barium, oh my god, barium nitrate and barium chloride. How would we do that? And let's see. Because these are both aqueous, we want to add something to not to make barium precipitate, because barium is common in both of them. My bad. I'm going to close my door. Okay, yeah. Barium nitrate. Yeah. So wait. Oh wait. So we're gonna add something that creates a precipitate with one of the what are these? These are ions. Yeah, one of the ions. Wait, not the ions. One of the non-metals. Hold on. Okay. One of the non-metals. So let's see. Nitrates, nothing is insoluble. Chloride, there's silver. So we can add. Ag. With Ag, well, I think it is. Yo, I deserve a pure table. Ag is silver. I'm always right, yeah. Chloride. So if I add that, barium will add Ag. Chloride will become not chloride, because barium. Okay, it works, but if we do NO3, we'll create the same one, and it'll make it easier. Yeah. So then barium becomes NO3 2, and then silver becomes chloride. Oh my gosh, this is the end. Okay. What's going on? Something's going on with me today. Yeah. Maybe it's because of Friday. It's a Friday. Okay, you know what? There. AgNO3 barium chloride becomes that. So that is right here, and that is aqueous, and that is the precipitate. So this is solid. So let's balance it, because why not? Yeah. So this is just double, and this is double. Okay. And that means this proves that barium chloride exists in the solution, and with lastly this left, you can, how would you do that? Hmm, because no nitrates actually precipitate. Uh, uh, and it's soluble. We can't really test it, but then can we use color? We might use color. We can't use color. Never mind. We can just use, I don't know, pH papers or something to prove the last one. But it's not that deep because we've identified 4 of them. Oh, next. Where distinguish between solid samples of the following. Yeah, it says distinguish between solid samples. So this will stay a precipitate, which is not that common. So we've proven that this solid, one mixed in water, becomes aqueous the whole time. So we've proven it as well. So we can write by dissolving in water, proven prove barium and 3 2. Okay, that's it for this question. It's kind of confusing because it includes like 3 tests, but it's just a question to prove that we know the tests and how they work. So it's a valid way to do it. I'm definitely not wrong. Now we move on to the next question. Next question is not that bad, so it tests us on using the equations of the aqueous solution chapter topic. Okay, same thing. So it says 25.6 grams of anhydrous sodium carbonate. So that means it's just sodium carbonate without any carbon without any water on it or hydrogens. Water, no water on it. So it's just Na and carbonate. CO3, the 2, no, it's 2. It'll be sodium carbonate. Sodium carbonate would be Na3, 2, yeah, right. There's 26 grams of that dissolved in 200 milliliters of water. And then part A, 200. Part A, want to calculate the concentration of moles per liter of this solution, assume no volume change. So concentration in moles per liter is equal to moles over liters, which equals to number of moles. So number of moles equals mass over molar mass. So then that equals to N over L equals to mass. So 25.6 divided by molar mass, which is sodium is 22.99 times 2 plus carbon is 12.01 plus 16 times 3 all over 0.2, and that, let's get a calculator, see what I get, divided by 22.99 times 2 plus 16 times 3 divided by 0.2, we get 1.20766611, which equals to 1.2021 moles per liter. That's it for the first question. And then part B, it says a 20 milliliter of the sample of the solution, which is this, solution placed in a 150 milliliter flask and 80 milliliters of water is added. Determine the concentration of the sodium ions in this dilute solution. So the important part is of the sample is 20 milliliters of the sample and 80 milliliters of added water. 80 milliliters of added water. And 150 milliliters flask is just showing us that everything fits. I don't think it's that important. So first we want to find how many, and we want us to calculate the concentration of sodium ions in this dilute solution in the end. So first we want to find the moles first, and then we'll put it in a new concentration, because this is the concentration right now, but we want a new concentration, so we'll make into moles first. So because concentration equals moles over liters, we want to find moles is concentration times L, which equals to 0.02 times 1.21, and from the exact value on our calculators we can get 0.024153222 moles. And then we can time this by the final sample, which would not be 80 milliliters, but 80 plus 20 milliliters. So concentration, it's actually the concentration of the whole thing, which is Na2CO3, which equals to N over L, which equals 0.02 from writing the whole thing, 0.2 plus 0.8, 0.024 over 0.8, my god, 0.02, and that equals to 0.1. Divided by 0.1, we will get 0.2415322. So that's moles per liter. But we don't want the concentration of this thing. We want the concentration of sodium ions only. So we just time this by 2. So 0.2415 times 2, which we will get 0.483 moles per liter for the concentration of sodium ions in this dilute solution. Yep, that's it for these two questions on aqueous solutions. Alright, bye bye.